Good morning and welcome to the 15th and last episode of the FAÇADE webinar series. Today, myself, Dr. Laetitia Marrot, Marie Skłodowska-Curie Fellow at the InnoRenew Center of Excellence, will present the result of the FAÇADE project and also side results of the project, all related to the tailored properties of biocarbon. Okay, so I have, okay. The FAÇADE projects mean FAÇADE biocarbon-based anti-UV coatings to prevent deterioration of wooden buildings. This project lasted for 2 years, from 2020 until end of March 2022. I got a funding of 150,000 euros and I carried out the research at the InnoRenew Center of Excellence in Slovenia. And my mentor is David de Valence, that I thank today for all the support he gave me for these 2 years. So the facade is the envelope of the building. It's the part of the building that will be in constant interaction with the outside environment. So with the temperature, humidity changes, sunlight, precipitation, etc. And it will be also in contact with both biotic factors, such as fungi, insects, molds, etc., and abiotic factors that I mentioned before. And these two types of factors combined together will conduct to the acceleration of the deterioration of the facade. And the deterioration will include alteration of the color, surface cracking, change in glossiness, and increased surface roughness. And all of this will affect the facade performance and also the aesthetical perception of the building. This is true for any type of material that can compose the facade, but it is even more especially true in the case of wood, that is a natural material and that is made of cellulose, hemicelluloses, lignin, and extractive, because the lignin will be very sensitive to the UV solar radiation. It will absorb it, and this will initiate the weathering by photooxidation. So it will conduct to discoloration and then to loosening of the fibers at the surface, erosion, and with this erosion, it will make possible to have penetration of humidity in the wooden surface. So for all this reason, we try to limit this weathering effect, and for this we will use coating to protect the surface of wood. There are different ways of protecting the surface, but one of them is to use UV absorbers. So they will absorb the radiation and they will convert it into heat, and then this heat will be dissipated and will not damage the surface. So how to choose the UV absorber? You can choose depending on the stability of the UV absorber, the UV range that you want to absorb, and the type of material that you need to protect. There are different UV absorber, the organic ones that are generally present some issues with stability. Inorganic absorbers such as titanium dioxide, zinc oxide, etc. These inorganic absorbers are quite efficient, but they are not renewable, and also they cause some issues with the safety and health, because some of them were showed to be carcinogenic. And then you have another type, which is the carbon-based materials. And these carbon-based materials are efficient depending on the type of carbon that is considered. Also in sake of sustainability, here we will try to use biocarbon as UV stabilizer and study if it's adequate source of UV stabilization. So what do we call biocarbon and how do we produce it? Biocarbon can also be called biochar, and we call it one way or the other depending on the application. So here I chose to call it biocarbon. This is produced from waste and from byproducts. In this project, we considered several sources of biomass. The first one is hemp stems, because in Slovenia, hemp is mainly grown and used for cannabidiol application, which uses only the flowers, and the rest, so 2 to 4 meter high stem, is considered as a waste. So we would use this. We would use also beechwood chips from the wood transformation industry in Slovenia, but from the waste also. We also considered olive stones, byproducts from the olive oil industry, and also other type of biomass. And then we use this thermochemical process to transform the biomass into biocarbon. So a thermochemical process, you can see on the right a picture of the tube furnace. We will use a nitrogen environment and temperature ranging from 400 to 1000 degrees. And it will be classified as slow pyrolysis or carbonization type of thermochemical process. After we obtain this carbonized biomass, we will fractionize it. So we will grind it and sieve it into different particle size, and we can also further downsize with using ball milling in liquid state, and then we will dry the material to get a powder. So here I present the different type of equipment that we can use to characterize these biocarbon particles. First, we will characterize the composition by proximate and ultimate analysis. So we can get the fixed carbon, ash, moisture, volatiles, and also the elemental carbon, hydrogen, nitrogen, oxygen, and sulfur content. And generally, when we carbonize the biomass, we start from medium carbon content, and we go toward higher carbon content, and we decrease the hydrogen and oxygen content. So on the bottom left, you can see a typical Van Crevelen diagram, where we see that the higher the temperature and the lower the H on C and O on C ratio. And this will be important for some properties of the biocarbon. We can also measure the particle size, so measure the D10, D50, D90, and the mean size of the particles. We have gas adsorption, so with two different gas, nitrogen and carbon dioxide, we can get the surface area of the biocarbon and also the repartition of the pores, and define how much micro, meso, and macro porosities we have in the material. And the final analysis will be the Fourier transformation infrared spectroscopy. And we can get to the functional groups that will be at the surface of the material. In this project, facade project, the targeted property is the UV absorbance. Once we produced biocarbon at different temperature, with different heating rate, with different residence time, and we analyzed all this carbon. And for the same particle size, we didn't see any influence of the process on the absorbance. So the process did not have really an influence on the UV absorbance. However, we tried to use different particle size and to measure the UV absorbance. So we dispersed the carbon powder in different concentration in water, and we measured the absorbance of the solution. So here you can see 4 different curves. You have 3 curves related to the sieved particles. Red is the smallest particle size, then gray, then blue. And the black one is a ball milled one. And you can see that first, the absorbance is dependent on the concentration. And there is a linear relation between the absorbance and concentration of the solution. And then that the smallest the particle, the highest is the absorbance. When we got to the ball milled particle, they were so small compared to the other that for equal concentration, we could not compare the absorbance. So here on the 3 different graphs, the ball milled particle, the concentration is more than 2 times lower than the sieved ones, and the absorbance is higher for all the different concentration. So what is controlling the absorbance is the size of the particles. Knowing this, we decided to coat the different wood substrates. So we used hand coating. We used tung oil as a film former. Tung oil is a natural oil, vegetable oil. And we used 2 different wood species. We used oak and beech. And we took, of course, this, the smallest particle size. And we used different biocarbon content ranging from 0, which means tung oil alone without biocarbon, to 20% biocarbon. So you can see on the left the different samples. And then we studied the weathering effect by leaving this sample on the roof of our new building. So you can see the little white spot in the middle of the picture. These are the samples. And on the picture, it looks very nice weather, but they were left for 5 months now during the winter. And this is what the sample looked like after 5 months, so beginning of February on the right. Now, how to quantify the changes of this sample and of the coating? We use different characterization. First, the color measurements. So we use a CLab system, which takes 3 different indicators. The L is lightness of the color, so more dark or more clear. Then you have the A, which is from red to green, and the B, which is from yellow to blue. And I chose to present here the total color change. So it means how the color changed between the beginning and the weathering time. So every month we did the measurement of the color change. And here you have the results for oak and beech. you can see that there is the same trend for both type of wood. The reference is in blue, and the reference, the total color change is only increasing. So the more the time passes and the more the color is changing. When you add the oil without biocarbon, you have the same tendency. The color change is always increasing. And this is not really surprising, because the oil also at the surface is also affected by the UV, and it turns more and more yellow. And you have also start to have the growth of microorganisms at the surface. And then you can see that for the different samples with 5, 10, and 20% biocarbon, there is a stabilization of the color. And the color change is very, very small, even after 5 months exposure. Then we looked at the wettability of the surface. We look at this using the water contact angle. So on the top right, you can see a drop of water deposited on the surface. And we are measuring the angle that makes the drop with the surface. So the lower the angle, the more hydrophilic is the surface, the more the water can be absorbed by the surface. You have the results here for oak and beech, and these results that you see now, it's with weathering, but inside. So we have samples outside on the roof, and we have control sample inside in the lab. And every month we are measuring the water contact angle for the samples outside and for the sample inside. These are the sample inside. For the sample inside, for the reference, for the two different wood, the water contact angle is stable with the time. And you can see that for all the other, even for the coating at 0% without biocarbon, you have an increase, a slight increase of the water contact angle over time. This is due to the choice of this tung oil that is reticulating with the oxygen ambient, and that keeps reticulating over time and keeps increasing the hydrophobicity of the surface. When you compare tung oil alone or tung oil with biocarbon inside, the biocarbon increase even more the hydrophobicity of the surface in both cases, for both wood species. Then if we look at the dashed line now, are the samples that were exposed outside. You can see that for the reference wood, the water contact angle decrease a lot, even with the coating without biocarbon, this water contact angle decrease. And once we add biocarbon, it is more stable. It decreases, but less. It decreases less, and it decreases the less for the coating with the highest biocarbon content. Here you can see some pictures of oak that is not coated initially at the very left. So you can see that the surface is quite porous already at the beginning. And the second picture, it's after 5 months weathering when it's unprotected. So we can clearly see the erosion of the surface, and that the porosity is increased a lot. And the next picture is for 20% carbon in the coating. So we can see that with a 20% carbon, there are still some porosities at the surface. We did not manage to cover all the porosities of the surface. And after 5 months, it is this porosity is increased, even though we are using the coating. So to conclude, we managed to get sustainable coatings with promising properties. The decrease in particle size led to an increased absorbance in both the UV and visible spectrum. The coatings were useful to enhance the color stability and also the water repellence. And what we could do now, we could try to downsize even more the biocarbon to get nanoparticles. So we could hope that we can use less biocarbon for this, obtaining the same properties and manufacture coatings that would be more clear and less black. We could also optimizing the choice of the film former to have a film former that has stable properties from the beginning, and also control better the coating thickness to cover all the porosities from the beginning and increase the efficiency of the coating. So beyond the facade project, we looked at other properties for the biocarbon. Here I will present some work that were done in collaboration with the CIRAD in France, with the Institute of Protection of Cultural Heritage in Slovenia, and also ZAG Institute in Slovenia. We looked first at the calorific power through the higher heating value of the biochar for solid biofuel application. So when you look at the higher heating value of the hemp biomass, you get a result around 18-19 megajoule per kilo. And then when you get biochar from this biomass, you can increase the calorific power of the material. And the higher the carbonization temperature, the higher you increase the calorific power up to a temperature from 400 to 600 degrees. When we went to higher temperature, we got a stabilization of the calorific power, and we did not manage to increase it, and the yield was, on the contrary, was decreasing. So we recommended to use the hemp biochar for solid biofuel application only to 400 to 600 degrees. Then we look at the conductivity properties of the biocarbon, and we saw that from 600 degrees we observed very, very little conductivity. But when we carbonized at 800 degrees and above at 1000 degrees, we got biocarbon that started to be really conductive. And we looked at the properties and tried to understand what parameter was bringing this conductivity to the biocarbon. First, we looked at the composition. You have fixed carbon and elemental carbon in the table here. And you see that from 600 degrees on, the fixed carbon and the carbon content are stabilized. So we cannot attribute the conductivity only to the carbon content in the biocarbon. Then we looked at the CO2 adsorption. So the CO2 adsorption provides information about the microporosity of the sample. So we saw that the microporosity is increasing up to 800 degrees, and then it is decreasing at 1000 degrees. We related this microporosity to the volatile matter that is going away from the sample when we carbonize it. And this volatile matter start to stabilize from 800 degrees. So it was going in the same way as the microporosity. Then we looked at the microstructure of the biochar using Raman spectroscopy. And with the Raman spectroscopy, we didn't see any order of the structure until 400 degrees. But then from 600 degree and higher temperature, we started to see these G bands and D band that are characteristic of highly ordered structures. Even if biocarbon is a non-graphitizable carbon, when we increased the temperature, we were seeing the ratio of the D band on the G band increasing, which meant that we get a growth of edge-bonded graphite-like structure. And these aromatic clusters closer and closer to each other, so in good correlation with the microporosity that was decreasing at 1000 degrees, allowed an increased contact between the conductive clusters, and that's why we got the higher conductivity at 1000 degrees. Then on another property that was studied was the Voc adsorption of the biocarbon. It is done through the PhD of Marie Skłodowska-Curie, and she is considering functional coating for adsorption and also degradation of volatile organic compounds. We were very happy to see that the biocarbon that was developed at InnoRenew was able to catch toluene and then to depollute the chamber from organic compounds. Then the last topic that I would like to talk about today is the valorization of the byproduct of the biocarbon. So biocarbon is already produced from waste, but then when we produce the biocarbon, we get this solid part, and we produce also some volatiles that are going out of the tube furnace and that are trapped in water bath, as you can see on the picture. So the molecules that are going out of the samples, they are trapped in these different fractions. Here we separated the fraction depending on the temperature of carbonization, and we collected this different fraction. This work is done with two of my colleagues, so Mariam and René Herrera, and also in collaboration with Christine Mail from the Institute of Wood Chemistry in Latvia. And together we are trying to valorize these water stream that are producing when we are producing the biocarbon. So once we have this fraction, we try to separate the components that are in the fractions using flash prep chromatography and different type of eluents. And then we identify the components that are in the different fractions thanks to Lcms. And we characterize the total phenolic content and the antioxidant activity of the different fractions in the view to valorize them. So the general conclusions of this presentation are that we investigated several properties: UV absorbance, calorific energy, conductivity, VOC adsorption, etc. There are more. We are also studying the addition of biochar in hemp PLA composite and looking at the influence of the biochar on the mechanical properties of the composites, on their water repellents, etc. Each of the property can be tuned using different process parameters. And we are always following a zero waste approach. So using waste to create higher value products, and by creating this biocarbon, also valorizing everything, everything by also valorizing the liquid byproducts. So I would like also to thank all the different presenters from the FAÇADE webinar series that were presenting some great materials every month. So thank you to all of them. And thank you all for following the webinar today. And if you have some questions, I'm here. So I see, I will stop sharing and I will look in the chat. What is the UV stabilization mechanism of biocarbon, and does it perform better than ketonic if stabilizers? So thank you, Avinash, for your question. So the UV stabilization mechanism of biocarbon, to me, it's a physical screen. And that's why when we use smaller particle size, we can have a better repartition of the particles at the surface and a better screen. And that's how it works. How can we measure the DC electrical conductivity of biocarbon? What could be the reason for its electrical conductivity? The reason for the electrical conductivity, so I was describing them. It's the agglomeration of graphite-like cluster that are growing with the increase of the carbonization temperature. How we measure the DC electrical conductivity? We had a homemade system, so we were using cylindrical equipment with a conductive base and conductive top, and we were putting a powder inside this cylinder and putting a piston on the top and pressing more and more the powder. And so we were following the density of the powder, and we were measuring the resistance of the current through the powder. And that's how we measured the electrical conductivity. Other question from Arnaud. Thank you for an interesting presentation. Did you plan to make LCA analysis of biochar used as a coating? Okay, so thank you, Arnaud, for the question. Yes, we plan to make LCA analysis. We used power meter, especially for the carbonization equipment, because we need to use a high temperature. So depending on the temperature that we were using, we measured the power necessary to produce the biochar, and also to grind it afterwards. The LCA analysis is still ongoing. So yes, we are doing it, but it's not finished yet. Did you control the impact of the thickness of the coating? No. It would be something to really look at. Now we used hand coating, and hand coating was quite hard to control the thickness. We should try to use maybe roller coating, so that would be easier to control the thickness and to really look at the impact on the performances. Other question from Philippe. Thank you for interesting presentation and congrats on the finalization of the project. Thank you, Philippe. My question is concerning the polymer composition of the lignocellulose used for biochar production. Did you notice any differences in the performance based on different polymer composition concentration within the cell walls of the materials you use? Does it even matter? Yes, so it matters a lot, the composition of the biomass. So here in the FAÇADE project, we mainly look at the differences of the process parameters, only looking at one type of biomass. So it was only hemp stem that were carbonized. But for the other applications, so for example, VOC, adsorption, we used other type of biomass, and we really see an influence on the biomass precursor. But right now, I cannot tell you exactly thanks to which polymer we got such performance. Yeah, I hope to have more answer for this question in the future. Veerapandian, thanks for the nice presentation. What is the final composition that is suitable for coating? I see some distinct properties for 5% of biocarbon in the weathering study. Okay, so for the final composition suitable for coating, with these results that I presented, the higher the carbon content, the better the performances of the coating. So 20% was the best for the coating stabilization, the color stabilization, and also for the hydrophobicity of the coating. But of course, it has a great influence on the color because the coating are very black. But even from 5, 10, 20%, the color at naked eye is black, even for 5%. So if it's fine to have a black coating, 20% would be the best. Then, as I mentioned, if we manage to use, for example, to produce, which is a challenge, to produce nano-size biocarbon, then we could hope to reduce the carbon content that you need to put in the coating, and maybe to get a coating with the same performances, but more transparent. Another question from Arno. Did you think that your coating solution could be used as functional agent for compatibilizer in composites made with plant fibers and polymeric matrix? So I was mentioning that we are currently studying the addition of this biocarbon in hemp PLA composites. We did some tests and we are looking at the influence of the addition of biocarbon on the mechanical properties, on the immersion, the water absorption after immersion of the composite in water, and on the hydrophobicity of the surface of the composite. These tests are still ongoing, or the results are still ongoing, and I hope to be able to present them soon. But Arnaud, I'm not sure if it's what you mean by functional agent. I hope I answered your question. Another question from Vera Pandian: in the extractive study, how do you dissolve the gases from the furnace to analyze with Lcms and flash prep chromatography? So these gases, when they go out of the tube furnace, they are dissolved in water. So we have water solution. And then we separated them with different solvents. So we were considering ethanol, acetone, and also other type of solvents, and with different concentration of one another to extract the different components. But then for LCMS, other type of elements were also used, and I would need to check to tell you exactly which one we used. Other questions? If not, thank you again for being present today, for looking at, for following the results of the FAÇADE project. And thank you for following the FAÇADE webinar series. I wish you a very good day, and I hope that we can have contact in the future. So you had my email, and don't hesitate if you want to contact me to send me an email and or to ask me some other question if you have more by email. So I wish you a good day and see you again.